here we go. Again, if you're having trouble, first things first, okay, think about what am I asking you to find. I'm asking you to find the rate of change of surface area. So we're going to write out the surface area equation. The surface area equation is S equals 4 pi r squared. Kaboom. Oh, I'm not connected anymore? Oh, this is a pain in the butt. Let's see if this works. Does it say magic is about to happen?
Yep.
Yes. Okay. Okay. Is this still working?
Yeah.
I think it is. Okay. We're on board. When you derive this, we're just using the chain rule to derive everything because all these variables have their own little derivatives and you get this. Okay. Thank you, Josh. By the way, fun fact, did we talk about oranges and surface area?
No.
Okay. You can remember that the surface area of a sphere is 4 pi r squared. You can do this at home. Okay. It's extreme fun. Go buy the most spherical orange you can find. Okay. It'll look like this. Except it'll be orange. There it is. Okay. Do we agree that this is the radius of that thing? Do you agree that if you chop that orange in half along that line and put it down on like a sheet of paper and traced it, it would make a circle the same size as the sphere? True. If you did that 4 times, there's 4 of them. Look at them. 1, 2, 3, 4. They're all the same size, even though mine don't look like it. And you peel the orange will fill up all 4 circles. Because what's each circle? What's the area of each circle? It's pi r squared. And the orange peels like the surface area. So it'll fill up all 4 of them. 4 pi r squared. That's what it does. You know what I'm saying? Okay. Okay. Well, yeah, you got to peel it nicely. You know what I'm saying? Okay. Okay. You can eat the peel. I don't know. It's fiber. I had a student once that ate the entire apple. Like ate the whole thing. That corner was like, no, ate the whole thing. Oh, he might have probably threw the stem out. Ate the whole thing. Yeah, apple's disgusting. Okay. Let's focus. This is the worst video ever. Yo, we want to know the rate of change of surface area. We need the radius, that's here, and the rate of change of the radius, right? We need those 2 things. So if I was nice, I'd give you both of them, but I don't. Instead, I give you the rate of change of volume, negative 32 cubic feet per minute. It's negative because volume is decreasing. Okay? But since that's a rate of change, it's probably going to help me find the rate of change I'm looking for, dRdt. And I'm also giving you the volume itself at this point in time. And if you know the volume, you can find the radius. Okay? That's the whole idea behind this. So the volume of a sphere is 4/3 pi r cubed. Everybody okay on that? That's volume. If we derive that to get dV dt, and the whole reason I'm doing that is because I know dV dt. So if I derive it, that's going to bring up other rates of change that will help me find. So dV dt is 4 pi r squared dr dt. Okay? The problem is, I know dV dt is 32 pi, negative 32 pi. I don't know what r is. So that's a problem. And I'm looking for dr dt, right? That's what I want to know. But I do know the volume is 32 pi cubic feet. And so anytime you write an equation, I don't know if you think like this, but I mean, it'll help you out. In this case, when you look at the variables that are in that equation, just if you know one of them, then you know the other, then you can find the other one basically by algebra. That's what that says. If you know the volume, you can find the radius. If you know the radius, you can find the volume. Okay, that's exactly what that equation says to you. We know the volume, which means we can find the radius. If you solve this, you're going to find out that r is 2. Is that okay? I think you're going to find that out, right? What's wrong with this? Oh, because it's 32/3 here. That's what I was going to say. Something's wrong. There we go. Now r is 2. Can everybody feel good about solving that? Multiply by 3, divide by 4, divide by pi, get the cube root. You get 2. And once we know r is 2, that goes right down there in my dV dt equation because we're finding that. So now we divide by 4 and pi and 2, and that tells us that. What's dr dt? Something's wrong. Oh, it's 2 squared. I was like, what's going on? Okay, drdt is negative 2. And that's in feet per minute. Okay, so I plug it in, and now that I know drdt and I know r, I can drop them into what I'm looking for, which is dsdt. We get 8 pi r, which is 2, drdt, which is negative 2, and that's negative 32 pi square feet per minute. On board? Wait, what? Okay. What that means? On period? Don't know.
You have to say the love at the end. That's on period,
I feel like, never mind. Let's go over the trig homework. I put this answer key online. All right, just for you and for all the other students in calculus. Where is this? Related rates trig. All right, and let's pull up what? Something trig. All right. So I'm not going to do every single one of these, but I will walk you through a couple, all right? So this first one says I'm in a hot air balloon, and I'm moving horizontally at 400 feet is my height. So that's not changing. I'm moving horizontally, so my height is just staying 400 feet. All good? Okay. I'm moving at 35 feet per second. And I want to know how fast the angle of elevation to me is changing when I'm 500 feet away from you, like through the air. So, what that looks like here is this. We have this triangle. Okay? I'm up here. Let me grab this. I'm up here in this hot air balloon. This is me up here. Everybody okay with that? I'm moving this direction. What just happened? Get out of here. Oh, somehow I went to full screen. How do I get out of this? Oh, I sound like an old man. Guys, what just happened? No, oh, my keyboard's not connected is a problem. Yeah, gosh darn it. Dude, there we go. It is escape. I just couldn't hit it without my keyboard. Thank you for saving the day. Oh, Lord. Okay. It'll happen to you too one day, kids. You'll be old. Yeah. My name's Ji Young. That's my rap name. G Young. Lil G. Lord G, that's a good one too. I like that one too. Lord G, yeah. Okay. Alright. Yo, I feel like we're getting off topic. Does it make sense that if I'm moving 35 feet per second, dxdt is negative? It's getting smaller, right? I'm moving towards the person down here who was looking at me like, oh my. Okay? I'm in a hot air balloon. I'm moving towards them. dxdt is negative 35 feet per second. That's what that means. If you're moving, that's the side of that triangle is changing. Okay. By the way, you could also draw your triangle up like this. It's the same exact thing. Okay. It doesn't make the top one or the bottom one are the same. Yep. I'm asking you how fast theta is changing. So I'm looking for d theta dt. So we need to link theta to what we know the rate of change of, x. And I think the best way to do that is tangent. Because I know 400 is not changing. Okay. We all good? So, anyway, I'm just going to walk through this one. The rest are all very similar. We get this triangle going on. This is all written out right here, okay? But I use tangent theta right here. And I derived it. So keep in mind, if you derive tangent theta equals 400 over x, which is what tan theta is, the derivative of tangent is secant squared. And the derivative of this, remember, this is the same thing as 400 x to the negative 1. So that's negative 400 over x squared. dx dt. Yeah.
Do you have to use tangent?
Now you can use cotangent.
I use
Cosecant? Cosine? But then you have like x over z, which you're going to bring in dz dt. You can do that. So hold on here, guys. Look. You have several options for this triangle, which is right here. Okay, this side's 400, this side's theta, this side I call it z, this side's x, right? If you use cosine theta, which you can, that's x over z, and we don't know how fast z is changing, which is a problem. Okay, you are a silly goose. We could also have used cotangent of theta, which is probably a little bit easier because cotangent is x over 400. Yeah.
How do you get negative 400 over x squared?
Because we're deriving 400x to the negative first power, man. Okay, just power rule. Yo, cotangent works out a little nicer. Does it make sense that if you derive this right here, you get 1 over 400 dx dt? Like, x goes away. So we don't need to worry about that at all, which is kind of nice. All right. I use tangent just because you guys are used to seeing tangent more often than cotangent probably, but it doesn't matter. All those will work. Some are easier than others. Okay? So we get here, and now we got to plug in. Look, we don't know d theta dt, so that's going to be there. We're looking for that. I don't know x, but I told you in this triangle up here, z was 500. And I'm hoping at this point we all know if the hypotenuse is 500 and the height is 400 and it's a right triangle, the base has to be 300. Okay? So x is 300. That's squared. And dx dt is negative 35. It's okay? So the only thing we're missing is what is secant of theta squared. So we got to find that. But we just come back up this triangle. Look, if x is 300 and z is 500, secant's the reciprocal of cosine. Cosine would be 300 over 500, which is 3/5. So secant is 5 over 3. Y'all with me on that? We need to know what secant is. Cosine is 3/5. So secant of theta is 5/3. Okay? If you got a trig and you have this triangle, you don't need to worry about what angle it is. Just find the sides of the triangle you need. It's 5/3 and you're squaring it. So this is 25/9. Okay? And if you have a calculator, bully for you. That's excellent. Good job. If you don't have a calculator, we can simplify this out like this. You ready? We need to multiply by 9/25. You okay with that? So d theta dt is simply negative 400 times negative 35 times 9 all over 300 squared, means 300 times 300 times 25. Y'all see where that's coming from? I'm just writing all the terms there because things are going to cancel. What's up, Arya? So, do we agree we can cancel 100 out? I'm just showing you how to do this. 100 canceling out turns this into a negative 4, and it turns this into a 3. Doesn't matter which one you use. It's okay? Canceling out a 9 from the top down to the bottom cancels out 2 3s. So this 3 turns that 9 into a 3. And this 300 becomes a 100 and turns this 3 into a 1. Just division out, right? We can also cancel out a 4. This negative 4 can become a negative 1, and this can become a 25. And last but not least, we can cancel a 5 out from that 35. So negative 1 and 35 make negative 35 make positive 35, and we can turn this into a 7 and this into a 5. So the only thing left up top is really 7 times 1. That's 7. The only thing left on the bottom is 125, and that's radians per second, because the measure of the angles change. I know, right? All right, the other ones are all very, very similar. I put the answer key online. Again, I'll be here after school. I got to show you something a little bit new today, though. Yes, sir. Calc angles are always measured in radians, because if they're measured in degrees, the derivatives aren't the same, which is weird. Okay, they're close, but they're a little bit off. Like they need chain rule to happen. We'll go on that another day. Okay, so we're going to talk about shadows today. Okay, yeah, shadows. Like, Batman lurks in shadows. Shadows. Okay. Only because these are ridiculous questions, but we're gonna go over them anyway. One of these was on the AP test a couple years ago, like a long time ago, and they're in textbooks. Every calc textbook has a question like this about shadows. Okay, but there's shadows with like moving things and light. So let's talk about this. Like for instance, if I put my hand in front of the projector, see how big it is? It's a big old hand. Look at it. It's funny. But if I move it closer to it, you see how it shrinks. And I move it closer to the projector again, it gets big again. Okay. So basically, if something's moving, its shadow is growing or shrinking depending on where the light is. All right. Have you guys ever check out this amazing drawing? If this is a lamppost shining brightly in the night, yes,
It's beautiful.
thank you. And here's the ground. Boom. And here's a person standing here. Okay. Okay. So if you guys have walked at nighttime, I imagine your parents let you do that every now and then. Okay. Thank you. Have you ever walked past a like a lamppost at night, and the further you get away, the bigger your shadow gets? Yeah. The same thing happens in the evening, like in the summertime when the sun is going down, your shadow gets really big, and it's fun to make it dance around. You know, yeah, you guys do that like my little kids do. That's cool. Okay. Anyway, does it make sense? Does it make sense that if this was a person right here and they were moving this direction, that their shadow, oh no, that their shadow is right here on the ground? True? And the further they get away from the lamppost, the bigger their shadow is going to get. Right? Which means as they move, as they move, this distance right here changes. Their distance from the lamppost changes, right? Whether they're moving towards or away from it. And as that happens, this side changes too. I call that H for shadow. Okay, good. Thank you, Tori. Make sense? So if they tell you how fast a person's moving, they can ask you how fast is their shadow changing? Which again, not a great question for us right now. It doesn't make a ton of sense. Later rates matter somewhere out there in the world, I imagine. Okay. For right now, this is just, can you connect variables and derive them? Okay. These questions will always be very, very similar. Everybody on board with what's happening here? There's a person, they got a shadow, they're moving. Okay. So, the way it'll be worded, okay, with no flair whatsoever, is a 5 foot tall, okay, person walks away from a 40-foot lamppost for some reason. Okay? How fast is their shadow growing when they are, how far away you want to be? 30 feet. Good. From the lamppost. Okay. Walking at, what's a nice leisurely amble? 15 feet a second?
5.
At 5 feet a second. Let's not use, we'll use 5. 3. They're working real slow. 3 feet per
Wait,
second.
3 feet per second is
Do you think that's fast?
startlingly fast.
Fast or slow? 3 feet per second. Every second. 1, 2, 3, 4.
Oh, really?
It's not one step, Peyton. It could be 2 steps.
Oh, wait.
3 feet per second is not that fast, gang.
Maybe I'm just doing speed.
Yo. 1 foot per second. Let's just do it. Is there's 5280 feet in a mile. True. There's 3,600 seconds. With me? In an hour. What's that equal? It's just. Here it comes. That's 3,600 divided by 5280. So 1 foot a second is 0.68 miles an hour.
Is that a little bit? Yeah, that's
Cool. Does that make sense? So that's about like 2/3 of a mile an hour. Can we handle that? So doing 3 feet per second is walking about
Ambling.
2 miles an hour. There we go. It's about 2 miles an hour is what we're moving at. Okay? Not very fast. What's up? That's 1 foot per second. So times 3. What's up? Yeah, man. Anyway. Yeah, there's a lot going on there. Main question, how fast is H changing? Do you all see? X is the distance you are from the pole. H is the length of their shadow. We know dxdt because we know how fast they're moving. We want dHdt. So all we need, like all the other questions we've done, is an equation that has an x in it and an h in it. Sound good? For these questions, we are going to use this invisible line right here to make triangles. See those two triangles? A little one and a big one? Those are similar triangles. And similar triangles have proportional sides. Okay? That means that, oh, also, this is a 5-foot person, and this is a 40-foot lamppost, per the question. We could use either 5 over h is equal to, what's that 5 going to correspond to in the big triangle? 40, that's an easy one, over, it looks like it should be over x, but it's not, it's over the whole side, x plus h. Got you, okay? Now, in general, kids, I like to keep my variables in the numerator. So this is the same exact equation as this. Y'all with me on this? I like the one on the right better, because the variable's in the numerator. We don't have to do any kind of fancy thing, okay? So, although I made you write that, think about the equations before you derive them. Can you move them around and make it easier? Okay? Now, in this particular question, if it's a lamppost up in the air and you're asked about how fast the shadow's changing, they always boil down super duper stupid easy. So we can derive this the way it is if we wanted to, or we can cross multiply and do a little bit of magic. Okay, check this out. If we do a little cross multiplication, before, all I'm doing is simplifying this before I derive it, and this will behoove you anytime you have to do a shadow question with the lamp up in the air. Okay? So we cross multiply, then I can just go ahead and get these h's together. There's that. And then if you're feeling super frisky, you can divide by 35. You get that h is just 1/7 x. That's kind of nice. Can we handle that?
Did you divide by 35 instead of 5 because we're looking for 8? Or the derivative of 8?
Yeah, I went with the HT, okay. And you don't have to do that at all right now, but you can. But that means by super incredible calculus, the rate of change of h with respect to time is simply 1/7 times the rate of change of x with respect to time. Is that okay? And the rate of change of x with respect to time was 3 feet per second. Positive 3 feet per second. Remember, that's how fast they were walking? Again, if they're moving at 3 feet per second this way, then this side's getting bigger at 3 feet per second. Okay? So it turns out dHdt is 3/7 of a foot every second. What up? If you're moving away from it, from the light. Okay, so that's a different question. Here the lamp's on the ground, and I'm putting my shadow on the wall. Versus the question we're doing is the light's up in the air and your shadow's on the ground. It has to do with how much light you're blocking.
Did they teach us
The further away you get from it, you know what I'm saying? Like the bigger the angle is across your head, I guess, which causes your shadow to go further out. Okay? Pretty much so. If you're right underneath the light, your shadow is right below you. What? What's wrong? Okay, good. So, hey, let's make sure this makes sense here. Hold on. Sometimes they ask questions that involve this. It's all the same work, but let's make sure you understand this. You ready? H is increasing at 3/7 of a foot a second, okay? That is only this side of the triangle. How fast is X getting bigger right now? We do know. 3 feet per second. So this side's getting bigger at 3 feet per second, while your shadow's getting bigger at 3/7 of a foot per second, which means the whole base of that triangle, if it mattered, is getting bigger at 3 plus 3/7 feet per second. Because both pieces are growing individually. Is that okay? Okay, I'm only asking that because there's a question out there somewhere, it might be in a textbook or something, where the question was, how fast is the tip of your shadow moving? Like, for instance, something my kids like to do when I'm walking with them and we have shadows is they're like, I'm stepping on your head, and they step on the head of the shadow. Okay, it's very, very cool. If I was moving at 3 feet per second, as in this question, they'd have to be moving at 3 feet and 3/7 of a foot at the same as a second. That means 3 and 3/7 foot a second to stay on top of my head. Okay, which I imagine is what my 5 and 7-year-old are thinking about as I do that. Okay. Okay. Yeah, they're probably saying poop and fart and everything too. They like those words. Okay. I bet you do. It's still funny. Yep. Okay. Okay. Yeah, man, we got the snowball going. This class is sponsored by the Blue Snowball microphone. All right, check them out. So, one other kind of shadow question you'll come across very soon, as in tonight, when you do your homework, or when you think about doing your homework and don't do it. G Young. Okay. Oh, that's funny. Yeah. Okay. Good. Okay. Is you ready? This one makes even less sense than the one we just did. Yo, sometimes there's a lamp on the ground, like a spotlight. Okay. Kind of like the projector here, right? Bam, and then your shadow's on the wall. Okay. So if there's a lamp back here, shining on this shadow, and there happens to be like a 500-foot wall right here. Okay. Now, it doesn't matter how tall the wall is. It matters how tall your shadow is on the wall. So same thing. Look, if this is shining, you're blocking light like that, and that's where your shadow is. Everyone okay with that? Thank you, Peyton. Excellent. Now, your shadow in this case, so this is different than the last one, all right? So you got to separate, is the lamp in the air or lamp on the ground? Lamp in the air is a little bit easier, but this is not really that hard. Okay? Here's your shadow now. Boom. Here is our 5-foot tall person. I'm going to type up a question so we see what this looks like in words. Here we are. Let's see. Ekta is escaping from prison. Good, good, good. There's a spotlight on the ground behind her as she runs for the 200-foot prison wall. Great. Okay. The spotlight is, what do you think? 100 feet from the wall. So that's not changing, okay? How fast, Young G, how fast is Ekta's shadow shrinking on the wall if she is running at, how fast do you think Ekta is? So we said 1 foot per second is what, 0.6 miles? 2 feet per second. It's just sprinting very slow. Okay, let's go 10 feet per second. That's really not that fast. I always give it to her. Okay, 10 feet per second, and she is 40 feet from the wall. Can we handle that? Oh yeah, so good, so good. I'll write a book one day. So, do you all see what's happening here? Poor 5-foot tall Ekta is running this direction. As she does that, her shadow is shrinking. Okay. Now, what's different about this, on the last picture, let's scroll over there. The base of that triangle was changing. Like X and H weren't fixed. Matter of fact, as X got bigger, H also got bigger. You with me? If the lamp is on the ground, where did I put it? Right there. That distance right now, like I said in my amazing question, that's 100 feet. That's not changing. The bottom of it's not changing. But the height of it is. The shadow is changing on the wall. Everybody good? So, if I were you, I would call the side next to the lamp X. All right? And if that side is X, let's think about this. The other side, you can make it Y or its own variable, but you don't need to do that because if I told you X was 30, what's the other side got to be? 70. Very good math. If X was 60, the other side would have to be 40. If X is X, then this has to be 100 minus whatever X is, right? Okay. So again, we talked about this. When I told you what X was, you know how you knew the other side? That means you don't need a variable for it. There's an equation for it using X. Okay? You give it a variable, but that just makes things more complicated sometimes. Anyway, do we know if X is running at 10 feet per second, that X X is getting bigger, right? dx dt is 10 feet per second. Positive 10 feet per second because she's moving away from the lamp. Cool. And now we need, since we don't know how fast the shadow is changing, we're looking for dHdt. What is that thing? We need something that links x to h, and we're going to drive it. Okay? These are similar triangles as well. They just don't reduce down as nicely. So we have this option here. Oh, it says, by the way, when she's 40 feet from the wall. If she's 40 feet from the wall, what's x? 60. Okay? Yeah, so be careful about that. If she's 40 from the wall, x is 60. Okay, so we're going to use that. Now, we could either do this. We could do 5 over x equals h over 100. Everybody okay with that? Or we could do the reciprocal of that. X over 5 equals 100 over h. Both of them will work. Thinking ahead, though, if I derive the left side, h is going to go away completely. Like the derivative of this is 1 over 100 dH dt. Okay? If I derive the one on the right, this one, h won't go away. I'm going to get an h squared down the bottom and a dH dt, which we want. But I don't know what h is in this question. Cool? So I'd prefer it if I derived it and h went away. So I don't want to use this one. You could. It'll still work, but you're going to have to find h then, which is just an extra step. Okay? So if I derive this one over here, we get negative 5 over x squared times dx dt equals 1 over 100 dH dt. Then we're going to plug in all the stuff we know. Again, she was, I forget, 40 feet from the wall?
Yeah.
So x is 60. So negative 5 over 60 squared. dx dt, she's running at 10 feet per second. And that equals 1 over 100 dH dt. Okay? And to solve that, all we're going to do is multiply both sides by 100. So we're going to have 100, a negative 5, and a 10. You can multiply that all out if you want to, but I'd rather simplify with the denominator. The bottom is going to be a 60 times a 60. So right away, do you see that I can cancel out a 100? We cancel out two 10s, right? 10 times 10. If we take 100 off the top, goodbye, each of these 60s becomes 6. Because we're dividing out 10, a 10 and a 10, okay? Then I can take away a 2 from a 10, 5, and from here, 3. And that's the best we can do. And dH dt is negative 25 over 18 feet per second. And it makes sense that is negative because h was decreasing, we said, right? The further you get from the lamp, the smaller your shadow gets. Okay? And 25 over 18 is close to like 1.5 feet. A little bit less, but that's how fast that thing's shrinking on the wall. Okay? That's it. So I'm going to give you like 5 or 6 of these for homework. They're all very similar to this. That's it. Okay. Good talk. Let's